Okay, I hope the PPT is visible. In the last class, what we were discussing about was the structure from motion problem, or which is abbreviated as SFM. Right. So in SFM problem, what happens is, okay, it's called as SFM. That is the abbreviation for the structure from motion problem. So in this SFM problem, you have two or more images, and you try to reconstruct the 3D scene from these two or more images, and these images would be from different viewpoints, right? Different viewpoints, so you can say it is taken from different cameras, or cameras which are placed at different locations, right? So it is called as structure from motion because you have the motion information, in the sense you know what are the positions of the different cameras, or you can assume that, let's say you're taking one viewpoint from here, another viewpoint from here, another from here, for the same 3D scene. Then you can assume that the camera has been, it is equivalent to saying that the camera has been moving from the first position to the second position using a Euclidean transformation or a rotation or scaling. So just by applying a rotation or scaling, the camera matrix M1 can be moved to the position M2, and similarly you have the camera matrix M3 and so on, right? So it is equivalent to saying that you're moving the camera positions, and you're trying to take the images of the same 3D scene. Okay, and it's called a structure because when you're trying to reconstruct the 3D scene, it is basically the structure of the 3D scene that you're trying to capture, right? So it's called as a structure from motion problem. And in the structure from motion problem, you need not know the internal parameters of the camera, or the camera that you're using need not be calibrated. So the SFM problem can be categorized, or you can have three different cases. First is the case where, let's say you have an internally calibrated camera. Okay, that means you know the intrinsic parameters of the camera, and you are trying to do a SFM reconstruction, right? So in that kind of a reconstruction, you can call it as a Euclidean reconstruction because the internal parameters are known to us. Okay, you can say that it is equivalent. The reconstruction that happens is in the Euclidean space. Okay, and since the intrinsic parameters are known to us, we can work with normalized image coordinates. So we'll be seeing the details of this in the next slide onwards. Now the second case that we have is the completely uncalibrated weak perspective camera, right? So it's called as completely uncalibrated in the sense both the intrinsic parameters as well as extrinsic parameters of the camera are not known to us. Okay, and it's a weak perspective. We'll see what do you mean by weak perspective later. Okay, so here in the case of weak perspective, what we are trying to, or the reconstruction that we get would be an affine SFM, or the affine structure from motion, right? And the third case is completely uncalibrated perspective cameras. It's a fully perspective camera, and the type of reconstruction you get is a projective SFM, or the projective structure from motion reconstruction. So we'll be looking at all three of the cases one by one. So first we'll see what is the Euclidean SFM, or it is also called as the internally calibrated perspective cameras. So as I said, it's called as internally calibrated because the intrinsic parameters are known to us, intrinsic parameters of the camera. And basically when you say just perspective cameras, what that mean is a pinhole camera model, right? Now here these equations, we have already seen these equations. Now K is the intrinsic, K represents what are the intrinsic parameters, or basically the camera metrics with the intrinsic parameters. And the various intrinsic parameters you have are alpha and beta, which are the magnification factors. Then you have theta, which is the skew between the image axis. Then x0 and y0 are basically the translation translation factors, or the translation vector, which is used to move the origin of the image plane to the center of the image. And all these five parameters together form the intrinsic parameters of the camera. Okay, and what we are assuming is that we are generally assuming that there are m, m is a variable number. There are m perspective cameras which are used. Okay, and the value of m can range between 2 or it is 2 or above. Right, and we assume that there are n points in the sense n 3D points which needs to be reconstructed, right? So on the whole, what we have is m is the number of cameras and n is the number of 3D points that needs to be reconstructed. In the sense, we will have mn correspondences or correspondence point pairs, right? And along with this you also have known intrinsic parameters. So from this, what we are doing is what we have to do is, from the point correspondences that we have, we need to reconstruct this 3D point, right? And as said earlier, since we are working with internally calibrated cameras, we can work with the normalized image coordinates. Okay, in the sense, it is the normalized coordinates can be mapped to the general coordinates using the intrinsic parameter matrix here, right? So I can write p is equal to k p dash p cap, right? P cap here represents the normalized coordinate, okay, or the representation of the image point in the normalized coordinate, right? So if we can work with the normalized coordinate, then on multiplying with the intrinsic parameter matrix, what we get is, or we can express the same thing, the image point in the unnormalized or the general coordinates. Okay, so this makes the calculations easier. So therefore we'll be working with the normalized image coordinates. Okay. So this is again a point that we had discussed. So because the cameras are internally calibrated, okay, this would be the equation which maps the 3D point to the image point. So Pij is the image point. You have two variables here, I and j, because I can range from 1 to m, because you have m cameras or m viewpoints or m images, and j can vary from 1 to n depending upon how many 3D points we are trying to reconstruct, right? So this point Pij can be mapped to Pj. Pj is basically the 3D point that we are trying to reconstruct, right? So it can be written as image point is equal to the camera matrix into the 3D point coordinates, right? So here the camera matrix can be written as 1 by z RT, where R stands for the rotation matrix, T stands for the translation matrix, and Z is basically what is the distance of the point with respect to the camera. Okay, so this is how we write the equation for a Euclidean SFM, right? In the case of Euclidean, the structure from motion, this is how we write the equation, and this is actually similar to writing it as, if it is a normal pinhole projection camera, what we write is just P is equal to MP, right? Where M is the camera matrix, P is the 3D point. So instead of the camera matrix, you're representing it as 1 by Z RT. That's it. Okay. So here, when you're trying to do a Euclidean structure from motion, there is a natural ambiguity of the problem, or you can call it as the rigid transformation ambiguity. What that means is, so we've already seen the image point is mapped to the 3D point using this particular mapping equation, right? Now if I try to rotate or translate, or rotate and translate the 3D point here, what happens is it just brings about a change in the external parameters of the camera. It will not change the internal parameters of the camera, and therefore you can say it is equivalent to just rotating or translating the camera, but it is taking the same image itself. Okay, so I'll just repeat that again. What I'm saying is, if I'm trying to do some kind of a Euclidean transformation on the reconstructed point or on the 3D point, okay, then what happens is it changes the rotation and translation parameters in such a way that the camera metrics changes only on the rotation and translation parameters, or it does, or the change happens only in the external parameters of the camera, which means that it is equivalent to changing the position of the camera all the while it is taking the same image. That means the image point Pij, you'll get the same image point Pij whether you do a Euclidean transformation to, if you're doing a Euclidean transformation to this 3D point, okay? Or in other words, what I can say is that this image point is invariant to the type of the Euclidean transformation, any Euclidean transformation that is applied to the 3D point. Okay, so if you assume that, if I'm saying, if I'm doing a Euclidean transformation to Pj, what you can say is that it is also equivalent to saying that, let's say I have an actual position of the 3D point, and after reconstruction I have obtained, after reconstruction in the Euclidean space, if I have obtained another position, let's say it's called as P dash J, okay, another 3D point, reconstructed 3D point for or instead of this PJ, what happens is this PJ and PJ dash both have the same image point Pij, right? Because it is coming from the same image correspondences. So the mapping between this true reconstruction 3D point and the reconstructed 3D point you have will be in the Euclidean space, or basically the mapping will be a Euclidean transformation. So this is what you call as the rigid transformation ambiguity. And in the case of equation, you can represent it this way. So from this equation, if I am applying a rotation or translation, what I do is I introduce these two matrices. So on introduction of these two matrices, when I'm computing it, what I get is I'll get another matrix in this form where I can represent it as Ri dash and Ti dash. But the remaining here 1 by z remains the same, or the intrinsic parameters remain the same, and it is equivalent to saying that, okay, you have another rotation and translation vectors for this particular 3D reconstructed point Pj dash, but the image of that point would remain the same, or the image is invariant to all the Euclidean transformations that happen in the Euclidean. So this is with respect to the Euclidean structure from motion reconstruction. Okay, and this is called as a rigid transformation ambiguity. Okay, so here if I am applying a scaling factor, let's say it's an absolute scaling factor, which means that it is not any shearing process which is happening, it's a constant scaling that I'm doing to all the points, okay, constant scaling, then the same ambiguity applies here also. That means the scaling factor will not affect the image point, okay, as long as it's a Euclidean structure from motion. Okay, so here this corresponds to a well-known property over here, that is the size of the objects, okay, will depend upon how far or near it is with respect to the camera, or their distance from the camera. So normally in the Euclidean space, when you're trying to do a reconstruction, right, the objects which are nearer to the camera appears bigger or larger in size as compared to those objects which are much further away from the camera, right? And one more point you need to remember here is that I've told that M is the number of cameras that you have, right? And N is the number of image points, not image points, the 3D points you're trying to reconstruct, right? So therefore the number of image correspondence point pairs that you will be having would be Mn, okay? So you have Mn image correspondences, right, which is represented denoted by Pij, where I can vary from 1 to m and j can vary from 1 to n, right? Now for these there will be 2mn constraints. Okay, so if you look at the previous equation of the Euclidean structure from motion, the equation for Pij, if you are writing the equation, you will have 2mn constraints, and from these 2mn equations, that means the total number of equations you have will be 2mn, and from these the number of unknowns that you need to find would be one set of unknowns you need to find is 6m, in the sense m is the number of cameras, right? So for each of the camera metrics that you have, there are 6 unknown parameters, or 6 extrinsic parameters are there. 3 for the rotation and 3 for translation. Therefore, there are 6 extrinsic parameters for each of the camera, and therefore for all the cameras together you will have 6m. Okay, so there will be 6m extrinsic parameters or unknowns that you have to find. Along with that, plus you also have 3n parameters from the 3D point, because the 3D point is represented by xyj, right? So like that you will have the coordinates of the 3D points for n points, right? So therefore there are 3n. The total number of parameters or unknowns that you will have to calculate would be 6m plus 3n. Okay, and the number of equations that you'll be having in order to solve this would be 2mn, right? But what we see is that usually now we say that the number of linear equations that you have should be larger than the number of unknowns, right? So in this case I said we have 6m plus 3n unknowns, and along with that here we are subtracting it by 7. That is the number of unknowns which needs to be computed or calculated. From that you are subtracting minus 7. Okay, so why you are subtracting minus 7 is because earlier, just one slide away, we discussed that the images that we are obtaining from the reconstructed points, it is invariant to Euclidean transformation, right? So even if there is a Euclidean transformation which has occurred or which you are applying to the 3D point, but still the image point remains the same, right? So that means these seven is the degree of freedom which is associated with the Euclidean transformation. These 7 parameters need not be calculated. Okay, because it is invariant to the Euclidean transformation. You need not calculate the parameters which are associated with the Euclidean transformation. Therefore, you're subtracting the 7. Okay, so that means now the total number of unknowns that you have, or the unknown parameters that you have, would be 6m plus 3n minus 7, right? So these many unknowns have to be calculated in order to find the Euclidean SFM, right? And the number of equations that you have, linear system of the set of equations that you have would be 2mn, which is or which should be greater than or equal to the number of parameters, right? Now one thing you need to remember here is that here since what we have what we keep saying is that if the number of image correspondences that we are considering, or we are trying to the more the number of image correspondences we have, the better the reconstructed image, right? So what we are saying is, okay, let's say you have the you're trying to reconstruct a house, let's say. So when we are trying to reconstruct this, the more the number of image correspondences you can find from two or more viewpoints, the more the correspondences, the better would be the reconstructed image. So therefore, keeping that notion in mind, if we are trying to increase the number of image points, what happens is this equation over here, the left hand side over here, this also increases, right? So as this increases, what happens is, if you're trying to solve it as a system of linear equations, right, solving for these unknowns is going to be a very tedious task. So instead of going for trying to solve the equations as such, what you can do is you can try to formulate this as a minimization problem. Okay, so the same problem I can write it in this way. I can write it as a mean squared error problem, where I write Okay, so I'm trying to, this is 1 by mn for the normalization, and I'm trying to minimize this particular error term. That means Pij is basically the point, okay, the correspondence point that we are taking. And here, this 1 by zrt pj is basically the estimated point. Okay, so we take the actual point and the estimated point, and we try to calculate what is the error, and we try to keep minimizing the error with different iterations, right? So the same problem, instead of solving it as a system of linear equations, what I'm trying to do is we can reformulate the problem using or as a minimization problem, where you try to minimize what is the mean squared error between the actual points and the reconstructed points. Okay, and this is how you get the equation. What we were speaking about was the Euclidean structure from motion. Okay, that means how we can try to create or reconstruct the points within the Euclidean space. And because it is within the Euclidean space, what we are saying is that the points or the image pairs that you have would be invariant to the Euclidean transformation. Okay, and now what we are going to discuss is how we can compute the projection matrices of the cameras. Okay, so in order to measure the projection matrices of the camera, we know that the internal parameters are known to us, right? Because what we are dealing with now, or what we are studying, is the first case, which is the internally calibrated camera, right? And in the internally calibrated perspective camera, what we have is the internal parameters which are known to us. So usually if the internal parameters are known to us, what we do is we usually go for the for finding the essential metrics, right? We try to find out the essential metrics from the internal parameters, and then from that you can find out what are the camera matrices. So let's say we are representing the camera matrices by m and m dash. So from that we calculate m and m dash, and then from this you can calculate what is the 3D point which needs to be reconstructed. So this is the method that we usually follow if we know the internal parameters of the camera, that is k. Okay. Now here, this problem of trying to find out the epipolar geometry. So here when I say epipolar geometry, what I mean is either the fundamental matrix or the essential matrix, right? So this problem of trying to find the epipolar geometry from the point correspondences that we have. So basically what we have first is the point correspondences here, right? PP dash. So trying to find that from the essential matrix from the PP dash or the image point correspondences is what you call as a calibration problem, or a weak calibration problem. Okay, and we will see how this weak calibration is done. I mean, this is something which we have already discussed earlier. It's the same steps. We'll just revisit those equations again. Okay, so here what we first do is we need to find the essential matrix, right? So in order to find the essential matrix given PP dash, so P and P dash are the image correspondent point pairs that we have. If you are assuming two images for the time being, P dash is the image correspondence pairs, and therefore I can apply this equation P transpose E P dash is equal to 0, from which I can find out E, which is basically the essential matrix, right? And in order to do that, I need to have minimum of 5 correspondences, okay, out of which 4 should be or should not be collinear, right? Now what we call this is a 5-point solution, because we have at least 5 correspondences, right? Now from these we are trying to, what we are trying to do is from these 5 correspondences we are trying to now this is minimum 5, so it can go even beyond that, and we are trying to directly put this into this equation and trying to solve the system of linear equations that we get, right? But what we see is that by using this direct solution, even though it sounds like it's easier, when you're trying to do the calculation, it's going to be a little difficult to do that. Okay, so instead of going for this direct method of calculating the essential matrix, instead what we do is we just take a longer route, okay, or we go by an indirect method where we first try to find the fundamental matrix F, and then from that we're trying to reconstruct the image in the Euclidean. So basically what we're doing is a Euclidean Sfm, right? So from this we try to calculate the Euclidean Sfm. So fundamental matrix, usually the fundamental matrix is computed or calculated if the internal parameters are not known to us, right? So when internal parameters are not known to us, that is when we try to calculate the fundamental metrics. So what we are assuming is that we are assuming the internal parameters is not known to us, and then we directly try to calculate F, or the fundamental matrix. And from the fundamental matrix, so this is how it goes. You have the fundamental matrix which is calculated. From the fundamental matrix, you try to calculate the camera matrices M and M dash. Okay, and from this we are trying to calculate the 3D point pre, right? So in the previous case we saw that when we are in the previous case it was like this. You have the internal parameters from which you are calculating the essential matrix, okay, from which you are calculating M and M dash, okay, and from there you are calculating P, and that P will be in the Euclidean space, okay, because here this E is used because you have these internal parameters. But in this case, since you are calculating the fundamental matrix, assuming that the internal parameters are not known to us, and then from there you are trying to calculate the camera matrices M and M dash, and from that you are trying to reconstruct the 3D points. So since the intrinsic parameters are not used anywhere here, the type of reconstruction that you get here is basically in the projective space. Okay, so I can represent this as the projective space. This is basically in the projective space. Now, what you do is once you get the reconstructed 3D point in the projective space, I try to include the information regarding the intrinsic parameters of the camera, and then convert this, or I can rectify this to a Euclidean space reconstruction. Okay, so like that I get the Euclidean Sfm. Okay, so this is kind of a slightly longer approach as compared to this, because here it's a direct estimation of the Euclidean 3D reconstruction. Here it's an indirect approach, but still this gives us practically this gives us a easier approach of solving the equations. So in order to find the parameters, right? In order to find the parameters F, what I do is I make use of this equation. That is, I write P transpose F P dash is equal to 0. Or if I try to substitute for P, let's say the coordinates of P is given by UV and 1 for the homogeneous representation. So I have UV1, P dash would be U dash V dash 1, and F, the fundamental matrix, can be represented as elements F11 till F33, right? So here the degree of freedom for the F or the fundamental matrix is 7. So you need to have at least 8 point correspondences Pj, Pj dash in order to solve this as a system of equations over here, right? And this set of equations that you have, that is P transpose Fp dash given by this equation is equal to 0. This equation, we can rewrite it in the form of UF is equal to 0, where U is basically unknowns, a set of unknowns, and U is basically a set of knowns, and F is basically the set of unknowns that you have. That means this F11, F12 is basically the unknowns which has to be computed, right? So those unknowns can be represented as a column vector here, F, and all the remaining vectors that you have, right? All the remaining ones, the known quantities, will go under the matrix U, okay, and we can represent it as UF is equal to 0, and then we can try to solve that particular equation. So rewriting it, this is how we can rewrite it. I can write f, which is the column vector having all the unknowns f11 to f33 as like this. And for the unknowns, for the knowns, I can write it as in the matrix form, which is given by x1, x1 dash, x1, y1 dash, etc. Okay, so these are the various elements of the matrix U, and if I try to solve UF is equal to 0, I can find out the fundamental matrix. Okay, and this has been derived from this basic equation which we have studied earlier, which is P transpose F P dash is equal to 0. So the problem of, again, as I said earlier, if you're trying to solve this problem, UF is equal to 0. Okay, if you're trying to solve this as a linear, as a set of linear equations, again, it can get the problem can get larger, because the more the number of 3D points that you're considering, that is, the larger the value of n that you have, again this matrix keeps getting bigger, right? And therefore solving it as a linear equations over here becomes difficult. So instead what we can do is we can reformulate this as a minimization problem. So how we reformulate this as a minimization problem is you can just try to minimize this term UF square, right? Or equivalently, it is the same as trying to minimize this term P transpose FP dash is equal to 0, or you're trying to minimize this particular term here, right? So basically what you're trying to do is you're trying to minimize the expression for the fundamental matrix with respects to the correspondence point pairs. That means we are trying to, in other words, you can say you're trying to minimize how much is the distance between the reconstruction that is happening, right? Or I can rewrite this in this particular way, that is, I can write this as 1 by n sigma d square pi fpi dash plus d square pi dash fpi. Okay, now what this means is this d stands for the Euclidean distance, p stands for what is the point, correspondence point pair, what is the point that we are considering, and fpi is basically the epipolar line. Okay, it is the epipolar line which is associated with p dash, right? So if I try to look at what is the Euclidean distance between the point, okay, that is the point on image plane, let's say the first image, and the epipolar line of the second image. Okay, so I can take the Euclidean distance of this and the Euclidean distance the other way around. So I have one image over here, I have another image here. Okay, so the first image I have this particular distance which is calculated to the epipolar line, and for this image you have the second distance which is calculated to the epipolar line here, right? So what I can do is I can just try to minimize what is the reconstruction which I'm trying to do here, right? So this is another way of writing the previous equation. Now here what happens is, now we have seen three different equations by which we can try to minimize the error. And but one point you need to remember is that it's very important to normalize the equations before going further, or before processing it further. That is, like, for example, in this particular equation, let's say you're assuming that you have an image, okay, and in the image, let's say you are having around the dimension of the image, let's say, is around, okay, 1000 cross 1000. Okay, that means let's assume that for this image there are 1000 rows and 1000 columns. So if you have such a large image, okay, or the image is, it can get even larger than this. So let's say you have a large image with 1000 cross 1000 pixels. What happens is, when we are trying to find these values over here, right, these are basically the locations of the pixel point pairs. So this locations, since we are trying to multiply the let's say you're starting with instead of 0, let's say you're starting with 1. If that is the case, then I can say the smallest value this matrix can have would be 1 into 1, which is 1. And the largest value it can have is, let's say you are trying to compute a position over here, right? So the largest value it can have would be around 1, 2, 3, 1, 2, 3. Okay, so you can have this large value over here, right? So that means I have values which is ranging from 1 to around 10 lakhs. Okay, so that means you can have very large quantities or very small quantities when you're working with the actual image coordinates or the actual number of pixels over here, right? So when you're working with the actual number of pixels over here like this, what happens is when trying to process the image or when trying to do this trying to solve this equations, the larger numbers would tend to dominate over the smaller numbers. That is the presence of the or those components or those unknowns with which it is associated with, the larger numbers are associated with, will have more influence or over the other ones. Okay, or you can say the other components would be, it will be equivalent to having a 0 or near to 0 because of this large value of the coordinates that you have here, right? So what happens is, because of this invariabilities or because of this large differences in the values or the entries, you can say that some of the components may have more dominance over the others. So that could cause a lot of errors in the reconstruction. So to avoid that, what we need to do is we need to do a normalization. So in a normalization, what we are trying to say is that you're trying to restrict this range of values which can be assumed. Okay, you're trying to restrict the range of values within a particular, a smaller range such that we are, trying to prevent the dominance of certain values or factors over the others. Okay, so that is why normalization is important. It is important to do normalization before we go ahead with the SFM. Okay, and this was proposed by Hartley 1995. He has proposed one way of normalizing. So what he has suggested is, first, you can go ahead with normalizing by going ahead with translating the origin. Okay, so you can take the origin such that the correspondence points that you have would be concentrated around the origin. Okay, and then you can scale the values that you have in such a way that the average distance to the origin is around square root of 2. Okay, so there are various types of normalizations that can be done. So we just go ahead with Hartley normalization, where this is the kind of normalization that you do, where you translate the data such that it is centered around the origin, and you scale the data such that here the average distance is given by square root of 2. And by doing this normalization, what we say is that there would be a great improvement in the reconstructed point that we get. So an example is shown over here. So in this example, if you see, this is an image without normalization, and this is an image with the normalization happening, right? So in these two images, what you see is that, so here, as I said, it is without the normalization, right? So without the normalization, if you see what is the mean distance between the point and the corresponding epipolar lines, you get the mean distance as 0.96 and 0.90 pixels. Okay, but if you're doing it without the normalization, you see that it is around 10 pixels and 9.12 pixels. That means if you're not doing a normalization, the difference between the mean distances for these two images, it is almost 1 pixel. Okay, for this particular example. Whereas if you're doing a normalization, what happens is this distance is as close to 0.06 pixels. So you can see how much of difference would be there, because 0.06 pixels is one, and having almost 1 pixel, okay, makes a huge difference, right? So normalization would help to reduce the error of the reconstruction. Okay. So now what we do is we have computed the fundamental matrix F, right? So after computing the fundamental matrix F, what we said was what we are trying to do is trying to find out the essential matrix, right? So instead of going for a direct computation of the essential matrix, we are trying to first calculate the fundamental matrix and then compute essential matrix from that, right? So we can compute the essential matrix by using the internal parameters. So we know the internal parameters of the camera. So therefore it is easier to compute the fundamental matrix, right? I can just write E is equal to K transpose F K dash. Since K, which is the intrinsic parameters of the camera, it is known to us. On applying that to F, which has been just computed, you can easily calculate the essential matrix, right? Now once the essential matrix is known to us, from that here we know that essential matrix is related to rotation and translation by this equation. So I can write it as TXR. So here this is a skew symmetric matrix representation. So from this we can find out or we can compute R and T, which is the rotation and the translation vectors given E. Okay, and we here also we use that singular value decomposition method in order to find it. So once we have the rotation and translation, what we are saying is basically that you have reconstructed or we have obtained the structure of the object, right? So if we try to put all the steps together, what we have discussed till now, what we get is what we call as the 8-point algorithm for binocular motion estimation. So the 8-point algorithm, this is a summary of the 8-point algorithm. So what we first do is the Hartley normalization transformation, which is given by the matrices T and T dash, right? So that means by applying T and T dash, we apply or we are trying to normalize the corresponding point pair coordinates of the correspondence point pairs, right? Now from this, what we do is we try to use the equations over here. So now here, since it is transformed or normalized, I can represent it as P tilde and P tilde dash. Okay, so instead of representing PP dash, how we usually represent, I can give just a tilde representation to denote that this is the normalized coordinates, right? So from the normalized coordinates I can just use this minimization expression in order to find out what is F, right? Now after finding out F and using the singular value decomposition, I can find out what is F, or basically F tilde, because again it is in the normalized transformation or normalized space. Now from that I can get back the fundamental matrix in the normal space, okay, by just applying a reverse transformation over here or an inverse transformation here, right? So I get back the fundamental matrix. Now once I have the fundamental matrix, I can calculate the essential matrix, and from the essential matrix I can calculate the rotation and the translation parameters, and this is called as the Langevin-Higgin 8-point algorithm for Euclidean structure from motion from two image points. Okay, and this is an example of how the reconstruction looks like. This is just one viewpoint, this is from another viewpoint. So here, as I said earlier, the mean Euclidean distance, okay, between the reconstructed point and the ground truth point, it is 0.87 centimeters. So here we are representing it as centimeter because this is a Euclidean SFM, okay. So that means because it's in the Euclidean space, you know that the length and the angles are preserved, and therefore you can find out it in terms of the metric, okay. And given that the house is about 20 centimeter high, you can try to calculate what is the exact distance between the reconstructed and the ground truth point, and that could be represented in centimeters. But in the case of affine or projective transformation or projective SFM reconstructions, we'll be representing this unit as pixels. okay, because the centimeter or meter values would not be known to us. Okay, so here we can try to find out the error. We are trying to validate or evaluate the 3D reconstruction done by finding out what is the mean Euclidean distance between the reconstructed point and the 3D point, and that is given by 0.87 centimeter for this particular example. Okay, so 0.87 centimeter, if you look at the relative error, it is around 3.1% compared to the radius of the sphere bounding the points. So here again, depending upon what is the reconstructed image scene used for, the error margin which is tolerated may be different. Like for example, let's say you're doing some animation movies. So in an animation movie, what happens is this reconstructed images, the reconstructed structures for each of the image scenes, it should be kind of the points should not vary too much, or the error should not be too high, otherwise there would be a lot of mismatch between the whole when the image sequences are combined together, there would be a very large distance, right? I mean a very large ambiguity or very large error would be there when you're trying to combine all the reconstructed scenes. So therefore it is important to know what is the application that you use, and according to the application, the value that you have here or the distance that you have here may be acceptable or not acceptable. Like for example, as I said, if it's the animation movies, if you have an error of 1 centimeter, it may not be acceptable because it can give an unevenness in the motion of objects when you're trying to take a video sequence with all reconstructed images. Okay. So far, we have been looking at the internally calibrated perspective cameras. And internally calibrated means that the intrinsic parameters of the camera is known to us. And we learned or we saw that internally calibrated perspective camera is equivalent to doing a Euclidean SFM or Euclidean structure from motion reconstruction. Next, we will be looking at uncalibrated weak perspective camera. So it's called as uncalibrated because the intrinsic parameters of the camera is not known to us. Okay, so the parameters are not known to us, and it's called as a weak perspective. We'll see what do you mean by weak perspective exactly, that we'll see later. Anyway, this kind of uncalibrated weak perspective cameras, it's also called as, or this kind of reconstruction is what you call as the affine SFM or the affine structure from motion reconstruction. Okay, so we have earlier studied about the pinhole perspective cameras or the pinhole camera. Now, pinhole camera is one type of model of the imaging process, and there are various other models also, okay, which can model the imaging process. So some other or two other specific affine models that you have is the weak perspective model and the orthographic projection model. Okay, so basically this weak perspective means that it is instead of saying a pinhole projection camera, okay, it is just another modeling of the imaging process. Okay, so you have slightly different assumptions when it comes to the affine model. We'll see what those are. So in the pinhole camera model, we know that, okay, we have these, you have certain 3D points, and it goes through the pinhole, and then you project it onto an image plane and you capture that images, right? So in this case, it is the same thing. Only thing is here, let's assume that we are assuming at least two 3D points here. Let's say it is given by P and Q, right? And here the corresponding image of capital P, which is the 3D point P, is given by small p. This is the image, right, of capital P. And this capital Q, 3D point Q, gives me the image small q. Okay, and this pi represents the image plane, okay, which consists the image of this particular scene or object. Now, if I assume that this 3D points which needs to be reconstructed are lying in the same plane, if I assume that it is lying in the same plane, let's say it is denoted by pi naught, then what I can say is the distance that these points have with respect to the center of the camera, okay, is constant, and I can give that constant value as minus z naught. Okay, so if I assume that these 3D points are lying on the same plane pi naught, then it is lying at a constant distance from the camera center, which is given by, let's say it is given by minus z naught. So if that is the case, then I can rewrite the equations of the camera projection model in this form. Okay, that means see, I can write here x, okay, I can write x is equal to minus d, sorry, this is minus here, I can write it as minus d by z capital X, okay, and this minus d by z, okay, I can represent it by a small letter m, which basically represents the magnification, right? And here z is equal to z naught. That is, what I'm saying is d is a fixed distance, that is the distance of the camera center from the image plane, and this z naught is the distance between the 3D point to the camera center, and this distance z naught is assumed to be constant. So if this is constant, then I can write x is equal to minus mx, y is equal to minus my, where m are constant values, and I can call this m as the magnification factors. Okay, and this magnification factor is remaining as a constant, right? So okay, since you have the minus over here, okay, so here now one thing again you need to remember is this x is equal to minus mx and y is equal to minus my are basically the values, or these are the expressions, equations for the weak perspective model. Okay, because in the weak perspective model we assume that the 3D points lie in the same plane. Only under this assumption can we say that these magnification factors remains a constant. Okay, and this does not hold good for a normal pinhole projection camera. Okay, so this equation is specific to the what to say, weak perspective model. Now, another way of saying that the magnification factors is constant is I can say all the line segments in the plane pi naught, okay, over here are projected with the same magnification. So whatever line segments I have here, it would be projected with the same magnification. That is another way of looking at the weak perspective model. Now this weak perspective model, it is also called as a scaled orthography. There is another name which is given to it. And one property that you see here is when the scene depth is small relative to the average distance from the camera, the magnification can be taken to be constant. So if you look at a 3D scene, we can't really say if that 3D scene or all the points on the 3D scene will lie along a plane, right? If since it is a 3D scene, you can have points, okay, which are not lying along the plane. But what we are assuming is that, let's say if you have this image plane and the points are somewhere very close to the 3D plane as compared to the distance of the camera. So let's say the distance of the camera is too far apart, and this distance, or the relative distance of each of the points on the 3D scene is relatively very less, then you can assume that these lie along a plane. Okay, so under that assumption we can say that it is a weak perspective model and that the magnification can be taken to be a constant. Okay, And again, we can further, try to look at this problem as you can say, let's say it is in the normalized image coordinates. When you're trying to normalize the image coordinates, I can take m is equal to -1. So in that case, if I rewrite in the previous equation was x is equal to minus mx and y is equal to minus my. So in that two equations, I can substitute m is equal to -1 and I get these equations: x is equal to capital X, y is equal to capital Y. And this set of equations is represented, or this defines the orthographic projection. So in the orthographic projection, what we assume is that all the light rays are parallel to the k-axis. They are parallel to each other. At the same time, it is orthogonal to the image plane pi. So we'll be going or we'll be coming back to orthographic projection model later. Let's now focus on the weak perspective model, or which is also called as a scaled orthography, where we assume that the magnification is constant. So here, as I said, for the orthographic projection model, what we assume is that all the light rays are parallel to each other. In the sense, we assume that, okay, the image, if you are taking the image of point P, okay, you get it over here, and the image of point Q, you get it over here. Okay, and we are assuming that all these light rays are parallel to each other. Okay, or if you think of the camera pinhole projection model. In the pinhole projection model, what we assume is that you have these rays coming through the pinhole, right, and you have the image formed. In this case, what we are assuming is that all these light rays, they come parallel to each other, and then you have these image points which are obtained P and Q. Right, so this one we will see this case later. So in this case, it is it's a bit different from the pinhole camera projection model that we have discussed, but we'll come back to this later. Okay. Okay, now if you look at this particular image animation that we see here, we see that the background of the image keeps changing, right, and even in some of the images it is zooming in and zooming out. So one thing you observe over here is that irrespective of whether the background is changing, or irrespective of whether the camera is zooming in or zooming out of the image, still the size of this image is remaining the same. Okay, so this is one example of the application of weak perspective model. Okay, so in the weak perspective model, you can say that it is equivalent to saying that you're trying to the size of the object at the center over here, we are trying to maintain it to be constant when the background is changing. And how we are trying to make this constant is by trying to zoom in into the object at the same rate as the all the other background objects are moving out. Or you can say you're trying to zoom into the object at the same rate as zooming out of the background, right? So this is one example of the weak perspective projection model, and we will see one numerical representation of how the zooming in and zooming out happens. Okay, but just to make you understand, this is just one application of using the weak perspective projection model. Okay, so here, as I said earlier, for a perspective model, perspective camera model, or basically the pinhole camera projection model, we assume that all the all the light rays, or all the rays from the 3D point, it comes, okay, it comes through, or it goes through the camera pinhole, and then you have it here, right? So in the perspective model, you can assume that all these 3D points over here, it comes from a single point, let's say somewhere over here. Now when you're trying to increase this distance from the camera, what happens is, as you keep on increasing the distance from the camera, at some point you can say, so that means the camera is now somewhere very, very, very far away. So as it goes far away, you see that these lines kind of tend to be parallel, and at some point when the camera is at infinity, at you can say that these light rays seem to be coming parallel to each other. Okay, so what I'm saying is that if you go with this concept and assume that instead of this point at infinity, or instead of assuming that the camera center is somewhere within the coordinate system, if I assume that the camera center is at a point at infinity, and then I can say that these lines would be parallel to each other, right? So if that means from a point at infinity you're trying to get these light rays, so you know that these would be parallel lines over here, right? So that happens if we are assuming that the object that you're trying to reconstruct is very far away from the camera point, or increasing the distance from the camera is equivalent to also saying increasing the focal length. Okay, so this is one assumption of the weak perspective model, where we say that the parallel rays, it intersects at infinity, or you say that the camera center will be at infinity as the distance of the object from the camera increases to a large amount. And for the uncalibrated weak perspective case, we can say that it is equivalent to an affine SFM, or an affine structure from motion reconstruction, right? So just like how we say in the Euclidean space, here also you can say that applying the affine transformation to the reconstructed points in the affine SFM will not change the image. Okay, so we'll be coming to that later on. So here let's say you have the affine camera. Here the imaging rays become parallel as discussed earlier, and I can represent the camera metrics as k. K is basically the internal parameters, and this is for the rotation matrices that you have, right? Now or this is the affine, so therefore these are just the affine metrics that you have, right? Now if you are assuming that the rays are coming, or rays are parallel, or if I am assuming that the camera center is at infinity, then I can rewrite the expression in this way, where the last column or the last row is equal to 0 0 0 1 to represent the point at infinity. Okay, and accordingly the remaining part of the remaining part of the matrix can be written as M11, M12, M13, M21, M22, M23, and T1 and T2. Okay, basically these are translation factors that you have, and M11 till M23 gives me an M2 cross 3 matrix with rank 2. Okay, so when I'm doing this kind of an assumption, what happens is, again, the kind of when I'm doing the reconstruction, the processing steps, it becomes easier. Okay, so since, as I said, since we are working with the camera center at point at infinity, I have this last row this way, right? Now I can again represent that same equation in this form, where I say this is the non-homogeneous coordinate form, where I can say xy, okay, is equal to, given by the matrix M11, M12, M13 till M23, xyz plus T1, T2. Now let's say if I'm assuming a 3D point at origin, if I'm assuming the 3D point XYZ is located at the origin, that means now since this is non-homogeneous coordinate, at the origin means it becomes 0 0 0, then that means this whole term goes and xy will be equal to T1 T2, right? So therefore I can say the point T1 T2 is basically the image of the world origin, or the origin in the world plane. Okay, and the center of the affine camera, as we know, or as we have already discussed earlier, it is assumed to be at the point at infinity. And the affine camera has 8 degrees of freedom. You have 6 parameters over here plus 2 parameters here. So totally there are 8 degrees of freedom. Okay, and basically this equation, or in the non-homogeneous coordinate system, or the previous equation which was in the homogeneous coordinate system, both represents the weak perspective model. Now, here, what we are trying to do is the affine structure from motion. We are trying to see when is an affine structure from motion reconstruction required, or when is it preferred over a normal Euclidean structure from motion. Okay, or in which scenarios would we use an affine camera as compared to a pinhole camera, right? So you use a fine camera when you assume that the scenes whose depth or relief is small compared to their overall depth relative to the camera observing them. Okay, or you can say if you're assuming that the image rays are parallel, or that the distance between the different depths of the 3D points on the scene is very small as compared to the overall distance from the camera center, then you can make use of the affine model or the affine structure from motion, right? But let's say you have an image scene where the foreground objects are placed very close as compared to the background objects, or the distance between the different 3D points that you're trying to reconstruct is that relative distance is large enough as compared to the distance from the camera. Then in such cases you prefer a Euclidean SFM, or you prefer a pinhole camera projection model. In this case, a pin camera is not a good approximation. Okay, so you cannot use an affine structure from motion reconstruction for all case scenarios. You can use that only if the 3D points in a particular scene, the depth of these 3D points. Okay, so what you let's say you have certain 3D points over here. Okay, and just as I said earlier, it is lying, if it's lying almost along a plane, in the sense it is kind of centered around a plane over here, or the relative distance is very small as compared to the distance from the camera, then you can go for an affine reconstruction, affine structure from motion reconstruction. And the advantage of using an uncalibrated approach, okay, because the earlier case, that is if you're using a Euclidean structure from motion, or let's say a pinhole camera projection model, what you're assuming is that the camera calibration has been done, right? Or they are calibrated cameras, right? So there are a few advantages of using uncalibrated cameras over calibrated cameras. The first advantage is that it does not require a preliminary calibration stage. So if you are, let's say, working with calibrated cameras, you will have to do an initial calibration. In the sense, you need to find out what are the parameters, the camera parameters needs to be known, right, in order to find in order to find the remaining, or for the remaining reconstructions, right? Or let's say the camera is moving, right? In that case also we require an initial stage of calibration. Okay, but instead in this case, if you are working with uncalibrated cameras, what we see is that in such a case we need not calculate the parameters from the internal camera parameters. Okay, all the parameters that we require, all the parameters, structure and motion parameters that we require, we can calculate it directly from the affine space itself. Okay, so that would be one advantage. And later, if you want to rectify it to a Euclidean space, then you can add in additional constraints relative to the camera parameters, known camera parameters, if you need to rectify that to the Euclidean space. Okay, but the initial reconstruction can be done in the affine space. So that is one advantage of using uncalibrated cameras. The another advantage that you can have is that since here we are just saying that you can handle multiple images, because what we are saying is we are working with, as I said, you have m number of images that you're working with, and there are n image correspondence points. So these values are variable, right? So but still the model or the reconstruction process remains the same. So you can have multiple images which are reconstructed in a uniform way when we go about with the uncalibrated approach. So these are some advantages, but a disadvantage would be that the error that we get, the error of reconstruction may be higher than the for the uncalibrated approach as compared to the calibrated approach. Okay, but still you do have certain methods by which you can rectify those errors also. So when you're working with the affine SFM or the structure from motion, you can have or you can compute that in two different steps. Okay, so what you can do here is, so we as I said earlier, if it is affine cameras, we take the case of a scene, whose relief or whose depth is small as compared to the overall depth. Okay, in the sense, if you're comparing with the distance from the camera, okay, if you're comparing the distance of the image point, distance of the image point with respect to the camera, and if you're comparing what is the depth of the different 3D points on the scene, this, if this depth is lesser relative to the overall distance from the camera, then you can say then you can make use of the affine structure from motion, right? And what we saw was that we can assume there are m affine cameras for m different images, and we have n 3D points. Okay, and these n 3D points is given by pj, where j extends from 1 to n. Okay, and since it is uncalibrated, the intrinsic and extrinsic parameters are unknown to us, right? So when we are working with the weak perspective projection equations, this is a general expression for writing it. That is, I can write small pij is equal to capital M pj1, right? So it is the same as, the representation is kind of the same as that of the pinhole camera projection model, where we write p is equal to capital MP. Okay, but here the difference is that this value of M, or the camera matrix M, is represented in a different way. You have AI and BI vectors which represents the camera parameters. So this equation here, the image point, I can write it as Pij is equal to AIPJ plus BI. So here MI is equal to AIBI is basically the camera matrix for the affine camera. Okay, this is specific to the affine camera. Okay, so this is the same as that we saw earlier. Okay, so here let's say in the Euclidean space we saw in the Euclidean SFM, we saw that even if we are applying a Euclidean transformation to the 3D point, or to the camera matrix, what happens is the image remains the same. In the sense, the image points are invariant to the Euclidean transformations when it comes to Euclidean structure from motion. So in the same way, when you're working with affine structure from motion, right? Here also it is invariant. The image points would be invariant to the affine transformations. That is, let's say for example, I am applying an affine transformation which is represented by the matrix Q, capital Q. Okay, so for to the camera matrix, when I'm applying the affine transformation, so this is basically for the affine transformation. When I am applying an affine transformation to the camera matrix, let's say I get another camera matrix which is given by mi dash, and similarly I apply the same transformation to the 3D point P, and I get it as P dash, right? So on applying this, if I try to substitute that in the basic equation over here, okay, which is given by AIPJ plus BI, what happens is, now instead of mi I may get mi dash, and instead of pj I get it as p dash j, right? But the image point would remain the same in this case. So that means the image point that we get is actually invariant to any kind of affine transformations that may happen in the camera matrix or the 3D point. Okay, and this affine transformation would take this particular form where you have cd and 0 1, right? So always remember that the last component over here would be 0 1, which represents the point at infinity in that case. Okay, and cd can take any value over here. So this is the affine transformation matrix. So we will need this, we will need to use this matrix q later. So we'll discuss more on that later. Now here again, in the previous Euclidean structure from motion or SFM, we saw that the number of solutions 2mn was greater than 6m plus 3n. So in the earlier case we saw that it was 6m plus 3n minus 7, right? So that was for the Euclidean case, right? Now in the case of affine SFM, we see that here the number of unknowns you have is 8m plus 3n minus 12, because here now m represents the affine camera, right? The affine camera parameters, and there are 8 parameters for an affine camera. So therefore I have 8m. Now 3n, n are the number of 3D points that we are considering, and 3 parameters for each of those 3D points. And then you have 12 here. So you are subtracting minus 12 because there are 12 parameters which represents the general affine transformation, right? So since the image point is invariant to the affine transformation, I can subtract these unknowns with respect, or which represents the general affine transformation. So therefore the total number of unknowns that I need to calculate would be just 8m plus 3n minus 12. And this problem of trying to find the Euclidean, the affine structure from motion, we can compute that in 2 steps. Okay, so the first step would be that we can compute the affine shape, okay, by calculating the camera parameters and the 3D points. So first you try to compute the affine reconstruction, and then later you can add in some constraints, okay, and then convert that to a Euclidean structure. Okay, so we can kind of decompose it into 2 steps, where you first try to calculate what is the affine reconstruction, and then try to calculate what is the Euclidean reconstruction. So we'll see how how this is done in the next class. So just to summarize what we saw in today's class, we were discussing basically about the SFM. There are 3 cases of SFM, or structure from motion. The first case is the case where it is internally calibrated perspective camera. So since it is internally calibrated, we assume that the camera, or we know the camera parameters a priori, and the type of reconstruction that occurs is a Euclidean reconstruction. And we assume that even after applying a Euclidean transformation to the 3D point, the image point still remains the same. That means the image points in a Euclidean SFM would be invariant given any Euclidean transformations being applied to the 3D point. Okay, and we saw how many the number of unknowns that is required, and we saw how we can solve that. So basically, instead of approaching it as a system of linear equations, solving it as a set of equations, we can instead try to formulate that as a minimization problem. And we saw 3 different equations that can be used in order to minimize or formulate that as a minimization problem, right? And then so for the Euclidean SFM, what we did was, we first, instead of directly calculating, so since the internal parameters are known to us, we can directly calculate the essential matrix, and from that we can calculate the camera matrices m, m dash, and the 3D point p. But in order to make the calculations easier, what we do is we go for an 8-point algorithm approach. So 8-point because you need to have at least 8 points for that correspondence. And so what we first do is a normalization, right, in order to ensure that the errors are reduced. So once you do the normalization, you go ahead with taking the image point pairs and calculating the fundamental metrics, and from the fundamental metrics then you calculate the essential metrics, and equivalently the projective, the 3-point in the projective space, and finally by including the camera parameters, okay, you can convert that into the Euclidean space. Okay, so that is the 8-point approach, and we have seen the steps which is associated with that, and later we saw what is the affine Sfm. So affine Sfm means it is the uncalibrated approach, or uncalibrated weak perspective camera model is what you call as an affine Sfm, or you can say that you are using an affine camera. Okay, so in this what we are assuming is, for a weak perspective model, we assume that the image rays are parallel to each other, or we can say that the camera point center is assumed to be at point at infinity. So making use of this property or this assumption, we can try to change the camera metrics, right? By doing that, what we get is essentially an affine camera, and we saw how the affine camera can be, or what are some basic properties of the affine camera metrics, okay, in terms of the number of unknowns. Now, in the next class, we'll be looking at details on what is the step-by-step approach for doing an affine structure from motion. So after this, you have one topic under the SFM, uh, which is the third case, that is the perspective, the projection, projection SFM, right? And then we'll be continuing to the last topic of the whole course. And you'll be having your quiz at 5:30. Okay, so remember the quiz, you had 2 questions from the previous class, okay, because the quiz was not there. So you have 2 questions from the previous class, and you'll be having 2 questions from today's class. So there'll be 4 questions totally. And since none of the questions are numeric questions, you'll be able to complete that within 5 minutes. So the time for submission of the quiz is given to be 5 minutes from the time of posting the quiz. Okay, so I have scheduled the quiz to be posted at 5:30. If in case it gets delayed by 1 or 2 minutes, accordingly you'll get a grace time of that many minutes. Okay, so anyway, overall, try to submit it within 5 minutes. If you have any doubts, you can ask me now.